Hi guys, I'm going to give us our lecture on the introduction to climate change, the climate system, and climate forcing. And there's some lecture slides. I'll share those with you guys on PowerPoint or on CourseLink as well. But this is so that we can sort of listen to me as I talk about these things. So we're going to sort of do an introduction to climate change, talk about the climate system and the different components of that climate system and how forcing works within that climate. This is mostly from chapter 10 and or the lecture notes. And unless it's a specific page number in the chapter, just assume everything is from chapter 14. And then there's some things on weather systems we need to keep in mind. That's from chapter 10. All right, so when someone says climate change to you, I think lots of us have heard those conversations where people are like, well, it's cold today, where is global warming? Or there's that picture of Greta Thunberg and she's like all bundled up and everyone's like, there's something wrong with the global climate change protest if, she's all bundled up as if it's too cold. And I think this is where we need to spend a little bit of time thinking about what is weather and what is climate. And so the things that we've talked about so far in our class have really been about weather. So those are things that are happening over short time periods. So hours, days, weeks, months, even a couple of seasons would be something what we talk about in terms of weather. When we're thinking about climate, we're thinking about things on the scale of decades to centuries to millennia to even tens of thousands to hundreds of thousands to millions of years, looking at the history of Earth's climate since it started 4.6 billion years ago or so. So I think when we're talking about this in the next couple of lecture segments or mini lectures, we really need to have in our head, these are really, really large changes in climate that we're looking at. And to do that, I want us to think about the climate system as a series of different pieces. So we have the atmosphere, we have atmosphere, we have vegetation, the land surface, ocean, and ice. Each of those 5 things, write them down, 5 things, are components to the climate system. And I'm pretty sure you'll see a quiz question about the components to the climate system. And what are they? It's atmosphere, ice, ocean, land surface, and vegetation. So that's the middle part of our diagram here. We're going to talk about in this little mini lecture, we're also going to talk a little bit about the causes or the forcing mechanisms with respect to the climate system. So things like changes in plate tectonics, changes in the Earth's orbit, and changes in the sun's strength. So thinking about those forces that we're looking at. And each of those forces, and we'll see that they vary over time in terms of how long it takes for plate tectonics to impact components of the climate system. And then we'll see that there's a response in those various parts of the climate system itself. And those responses is that ends up producing our climate. There's a 4th force on here that's not in my little fancy diagram, and that's humans. And we'll spend most of our time in the last week of our class talking about humans as a forcing mechanism for climate. So climate system responses, this is something that's important to think about in terms of each of those different components and or a forcing mechanism. So the response time is the amount of time it takes for the climate systems, all 5 of those components, to react fully to some imposed change in the forcing. So in this case, in our diagram here, we can think about that forcing being the Bunsen burner and the response being the temperature of water in this beaker. The response time for various components of the climate system vary from hours to weeks with respect to the atmosphere. It's the fastest responding climate system, to things like the ice sheets and deep oceans that can take hundreds to tens of thousands of years to respond. And so because there's some components of the climate system that respond quickly or fast, and there's some components of the climate system that respond slow, it's possible that for one forcing mechanism, you might not actually see any kind of response at all. And that's why the deep ocean temperatures don't change very much with respect to daily fluctuations in incoming solar radiation. Because in order for the deepest part of the ocean to change in temperature, that incoming solar radiation has to make its way through the upper part of the ocean and then deeper, 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 and that takes time. And so we don't see daily fluctuations in deep ocean temperature because of that response time that's part of that. So because of that, we have things depending on the forcing and that the magnitude of that forcing and the response. So we have sort of these series of kind of responses and forcing mechanisms. So our top part of our picture up here is showing a slow change in forcing and a forcing mechanism or response that matches that. So they're going to sort of march along together that we see up here. Hopefully you can see my arrow pointing that out. So looking at, see if I can use my arrow. So pointing that along here. In our next one here, we have an example of a really fast change. So there's a sort of on-off forcing mechanism and a really slow response. So the magnitude of that response is actually quite small. And these last two diagrams here, we sort of see examples when that forcing mechanism is turned on and turned off. And depending on how long it takes for a particular component to respond to it, it ends up being a delay. So in this example, the third one from the bottom here, we have our forcing mechanism turns on, it's on for a little while, and then it turns off, where our response takes a little while to keep responding to that forcing mechanism, reaches its peak, and then the forcing mechanism is turned off and it starts to drop down again. So there's lots of examples of this in Earth's climate where we see these kinds of variabilities. So again, this is sort of taking us through these individual sort of slow change in forcing and a fast response. So an example of a slow change in forcing would be tectonic forcing. Those plates are moving around at a relatively slow rate, given to some of the speeds at which parts of the climate system respond. All parts of the climate system respond when you think about tectonic forcing. So this is something where we're going to see the slow change, and that sort of response is going to match that as it goes along, and it tracks that. Other examples where we have like really quick on and sort of off are things like volcanic eruptions. And that might be less for maybe a couple of weeks in the case of Mount Pinatubo in 1991. And then the impact of that was that the Earth's temperature dropped a little bit and it was low for a little while, for a couple of years following 1991. So again, in terms of the entire span of Earth's climate history, this is a really short amount of time, but we're seeing that change and using that as an example for a fast change in forcing and a slow response to match those two. And again, if those forcing responses are nearly equal, or we have that on again, off again kind of climate forcing switch, we see various intensities or degrees of response because of that. And that's what our last two diagrams were showing on that first page. The other thing, and again, we don't see those in that first diagram, is that really, rather than having sort of like a quick on, quick off switch with respect to that climate forcing, it might be something that cycles. And so in this example here, we have that heat is getting applied and that water temperature is slowly responding, and then that heat gets turned down, and then slowly our water temperature goes back down. And so that cycle that we see is something that's really common throughout the climate system and the climate forcing mechanisms. And then again, there's going to be interactions within those pieces. So an abrupt change in climate forcing can produce responses that are slow and fast. We saw that with respect to the climate system. So atmosphere might respond quickly, but the ocean might respond slowly. And that might lead to interactions within the climate system. So if the ocean is slow to respond, but eventually does respond, it's going to actually start to heat up the atmosphere. So we're starting to see forcing within the climate system due to these external forcing factors. And that's going to we'll see that sort of piggyback over time. We're looking at some of these examples in Earth's climate history over the next couple of mini lectures. So again, if that climate forcing is cycling and we end up with that cyclic response, we may end up with a bit of a lag between some of these things. So that initial forcing is here, that fast response tracks it. This could be like the ocean, or it could be like the atmosphere or the upper ocean, whereas the slow to respond is maybe the deeper part of the ocean. So it becomes a little bit out of sync between those things. And depending on where we're looking for evidence of change, we might see a lag or a delay in that impact or change in that fossil record or in the isotope record, wherever we're looking for evidence of climate change. Then there's, if that wasn't already complicated, we also have to consider feedbacks. And so we talked a little bit about that, where, you know, one input results in the output, the output of one instance becomes the input to another system. And so we start to see that often in the climate system. And we can talk about feedbacks as that sort of action and then a reaction. The other piece to that is that depending on the what happens in terms of that reaction and what system is getting impacted, that response might actually enhance the original condition, and that will be called a positive feedback. So when whatever the initial condition is, something happens because of it, and then the result of that, of what happens, like enhances that initial condition. And a negative feedback is one where that initial condition creates something that ends up actually dampening or slowing down that initial condition. And so that's a negative feedback. So positive feedback and negative feedback don't necessarily have to do with temperature changes or more or less rainfall. It's about an enhancement of the original condition if it's a positive feedback, and it's about the dampening or reduction of that initial condition if it's a negative feedback. And I think you can expect to see some questions about positive and negative feedbacks on the quiz that we have associated with long-term climate change. So again, thinking about those responses, you may have the interaction between, say, vegetation and land surface or vegetation and atmosphere might actually be an interaction that results in a positive feedback or a negative feedback. And all of that is going to depend on the forcing mechanism as well as the time ranges that we're looking at. So thinking about all this, I want us to think a little bit about those time ranges. So we're going to look at climate change over millions of years, hundreds of millions of years, hundreds of thousands of years, and then tens of thousands of years, and then thousands of years. And then in particular, we're going to focus on what's happened in the last kind of 100 to 150 years. That's going to happen in the last week of classes. So just to kind of give you a sense of that global climate dynamics time frame that we're looking at here, if we look at the diagram I have up, we've got just the climate change over the last 300 million years in this diagram. And we're going to go back further than that when we talk about all this. But that change that we see in just the last 300 million years, focusing on this diagram here on the left, we need to think about what's happening. So along the y-axis here is time. So we're going back through time all the way to 300 million years ago. And over that time frame, 300 million, starting 300 million years ago, it got almost 10 degrees warmer than it was 300 million years ago. And since about 100 million, maybe more like 60 million years ago, it's been getting gradually cooler with a couple of sort of like hiccups in that range. So the first thing to note for this part of the diagram is over a really large time frame, we've had pretty big swings in temperature. So over 300 million years, we're changing our temperature upwards of 10 degrees. That's the first thing to note. If we just zoom in on this top part here, just looking at the last, say, 3 million years, and it's like zoomed out here on this next diagram. So this is just the last, going from 0 to 3 million years. So it's as if we zoomed into this one little corner right here. We can see way more variability in the last 3 million years, but that the scale of that variability is not the same scale as the variability that we've seen in the last 300 million years. So we go much warmer to much cooler. We're kind of on the range of 5 to 8 degrees Celsius change, where this one is on the change of 10 degrees. So we've got back and forth in the last kind of 2 million years, and then the last 1 million years, we have these bigger sort of seesaw pattern coming all the way back, or zigzag pattern coming all the way back. If we just focus on what's happened in the last 50,000 years, that's this third diagram here. So just starting back 50,000 years, we've got a little bit of variability, and then it got a lot warmer, and then it's been a little bit variable in the last sort of 12,000, 10,000 years. Again, a couple of things to keep in mind here is the x-axis has changed on this one. So instead of going plus or minus 10, we're plus or minus 3. So the amount of variability has gotten smaller, and we've got the pattern isn't as consistent as we've seen in the past. And then finally, sort of the last two diagrams to look at here, if we just zoom in on the last 1,000 years, we see changes, again, much smaller temperature scale, about a degree, but we're seeing variability in the last 1,000 years. And then from the last 100 years, that trend, not so much variability, but the trend we've seen has been to be getting warmer in that last 100 years. Now compare all of that. So the scale we're looking at over hundreds of millions of years is 10 degrees. The scale we're looking at over 300 million years or 3 million years is like 10 degrees or almost 10 degrees, sort of 5 to 8. The last 50,000 years is 3 degrees. The last 1,000 years is 1 degree. Now just think about the temperature today. So the temperature to get today, this is Thursday, March 19th. Happy birthday, my brother. We've sort of seen it kind of go from a few degrees below zero to being a couple degrees above zero. So maybe like on the order of like 5 or 6 degrees total change. But some days it can be like, -2 to start and get up to +13 in March. So that temperature range that we see over a really short time period, like one day or a week or a month, that's weather. And so when we're talking about each of these panels here, 1, 2, 3, 4, these are things that we're looking at the average global temperature across the whole planet. And so that's what we're talking about change. We're not talking about at a given spot over a given sort of 24-hour period. We're talking about things over a much larger spatial scale when we're talking about climate. All right, so now I want to talk a little bit about climate forcing, and there's 4 categories of climate forcing, and we're going to talk about each of these individually in more detail. So we're talking about climate forcing in the scale of tectonic processes. This is really, 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 really slow. This is millions and millions of years. So the little animation that's running up here in the top right is showing us that the sort of change in where tectonic plates have been over the last 150 million years as that animation runs through. And that's taking a really long time. But as the mega continent breaks up, stretches out, and comes back together, which is what it'll probably do in the next 200 million years, it's changing our climate on our planet. So that's one of those forcing categories or forcing mechanisms. The other way we have climate gets forcing from an external mechanism is through changes associated with Earth's orbit. In particular, there's some things referred to as Milankovitch cycles, and we'll have a whole sort of mini lecture on Milankovitch cycles itself. But that's on the scale of tens to hundreds of thousands of years. So orders of magnitude smaller or shorter than tectonic processes. And then the next 2 are related to changes in the sun. So the strength of the sun can change in terms of the amount of solar radiation that's received at the Earth's surface. And that can happen both on the scale of sort of decades, so relatively short, all the way up to sort of thousands of years at a given time. So we'll look at some of the patterns associated with changes in the sun and how that impacts parts of the climate system. And then our last one is anthropogenic forcing. So this is really something that we're looking at over this, not part of the natural climate system, but something that we're just sort of focusing on the last 100 to 150 years. And again, all of these are a result of inadvertent additions of greenhouse gases to the atmosphere, or anthropogenic climate change, enhancing that greenhouse effect. So to summarize what we've talked about in this little mini lecture is we talked a little bit about climate and weather, what's the difference. And so in terms of the scale, like both the temperature scale, but also the spatial scale that we're talking about. Then we looked at climate system components and response time. So we talked about feedbacks. If there's a lag, so that quick response or a quick forcing mechanism and a slow response, or a slow forcing mechanism and a quick response, and the 2 match together. And then we looked at timescales of climate change. So going from sort of hundreds of millions of years to millions of years to tens of thousands of years to thousands to hundreds of years, and then the different forcing mechanisms. And that's it for this little mini lecture on sort of our intro to climate change. And I hope everything is going well. Take care, everybody. Oh, we're still recording. Oops. Now take care.